Next, we have Andrew and Peter presenting about Bayesian optimization using gradients.
Thank you. I'm Andrew Wilson.
And I'm Peter Frazier.
And we're going to be talking about how to use derivatives to speed up Bayesian optimization. This is joint work with Jian Wu and Matthias Polacek. Bayesian optimization enables global optimization of expensive multimodal objectives, whereby an acquisition function trades off exploration and exploitation. Bayesian optimization has many applications, including automatic scientific discovery, automatic machine learning and hyperparameter tuning, and automatic engineering control. However, unlike most optimization procedures, Bayesian optimization typically doesn't use derivative information, and we can imagine such information would be quite useful. If we wanted to help our friends in a scavenger hunt, we might say, look in that direction, or look in this direction, and hopefully they'd find what they're looking for more quickly. In this paper, we're focused on how to best use derivative information to help Bayesian optimization find what it's looking for more quickly. I'm going to start with a quick summary of some of the key ideas in the paper. Don't worry if you don't initially understand everything. We'll revisit many of these points throughout the talk. So Gaussian processes are often used to model our objective function in Bayesian optimization. And fortunately, Gaussian process regression can naturally accommodate derivative observations. In the figure on the left, I have a Gaussian process distribution over our objective, which has been observed at 4 locations given by the blue dots. The predictive mean of the GP is given by the black curve, and the predictive uncertainty is given by the shade. In the figure on the right, we've also conditioned on derivative observations, and we can see that this distribution over our objective has been significantly updated. However, it really matters how we use derivatives in Bayesian optimization. In the bottom row, left panel, we have exactly the same figure that we had on the previous slide before we've observed derivatives. In the bottom row, middle panel, we have 2 different acquisition functions, EI in green and KG in red, showing at their maximum value which point to query next in the optimization procedure, trading off exploration, going to where the GP has high predictive uncertainty, and exploitation, going to where it has a low predictive mean. In this case, both of these acquisition functions, KG and EI, are proposing similar query points. However, in the top row, after we've observed derivatives, we see that KG is proposing a very different query point, whereas EI is relatively unchanged. And as we'll see, this is partly because KG is anticipating the value of information in observing a gradient at the next time step. In summary, there's some exciting related work, and our contributions include a novel acquisition function that outperforms EI with derivatives, and a novel estimation of this acquisition function using the envelope theorem, batch evaluations, noisy and incomplete derivatives, and value of information-based retention of single directional derivatives for scalability, applications in kernel learning, logistic regression, deep learning, and k-nearest neighbors, further revealing where gradient information is most valuable, and a theoretical analysis of our approach to Bayesian optimization with derivatives, showing asymptotic consistency and one-step Bayes optimality. So let's again imagine that we have a Gaussian process distribution over this objective that we're trying to optimize, which we've observed at 4 points given by the blue dots. Now in the bottom figure here, we have our acquisition function, which trades off exploration, going to where the GP has high predictive uncertainty, shown by the shade, and exploitation, going to where it has a low predictive mean, in order to propose the next query point. In particular, here we have expected improvement, EI, a popular acquisition function, which maximizes the expected difference between our objective at the new query point and the current optimum. Here, EI is telling us to propose the next query point at the location of this red box. And when we do that, we update our posterior over the objective, and we also update our acquisition function. Now EI is proposing to move to the location of this red box near 1.2. Again, we update our posterior and acquisition, and we can continue until EI is saying there's not much utility in continuing the optimization procedure further. So as we said, GP regression can easily accommodate derivative observations, and we're focused on how to use derivatives to speed up Bayesian optimization. There's been a lot of exciting work recently showing how we can obtain derivatives for applications where it would be useful to use Bayesian optimization. For example, McLaurin et al. Make gradient information available for hyperparameter tuning in deep learning. Adjoint methods provide gradients for PDEs. We can also get gradients for expensive closed-form objectives, such as for Gaussian process kernel learning. And we can compute approximate gradients. However, as we saw earlier, popular acquisition functions aren't necessarily that responsive to the presence of derivative information. So Peter's going to talk about how we can do better.
Our core contribution is a novel acquisition function that makes better use of gradients in the context of Bayesian optimization. To explain this method to you, I'm going to ask you to do a thought experiment. Imagine that we've taken n samples of the function and its gradient. From these samples, we've computed the posterior distribution, and in that posterior distribution, we have the posterior mean, indicated here as a solid black line with the notation mu n of x. If we were risk neutral and we needed to report a solution to our optimization problem immediately, we would choose the point with the lowest posterior mean, and the value at that point would be mu star of n. If, on the other hand, we could take a batch of q additional samples, evaluate the function and its gradient at those points, we would have a new posterior mean, and a new minimum value of that posterior mean, mu star n plus q. The difference in these two minima would be the value created through sampling, the reduction in conditional expected loss due to sampling. Before we sample, we don't actually know what this value will be, but we know its distribution based on the posterior at time n. Our acquisition function is the expected value of this reduction in conditional expected loss. We call it the DKG factor. And our algorithm samples at the point that maximizes this acquisition function. Here's one way to calculate that acquisition function. Suppose you're given a batch of points at which we're proposing to sample. We'll simulate from our posterior distribution the value of our objective and its gradient at these points. Then, if we're observing with noise, we'll simulate the noise, add it to our observations. We'll then calculate what the posterior would have been if these results had actually occurred, calculate the posterior mean, and calculate its minimum, and that's mu star n plus q on this particular sample realization. We'll compute the difference between mu star n plus q and mu star of n, and that's the reduction in loss on this simulation replication. We'll average that many times. Now, while we could optimize the acquisition function, the DKG acquisition function directly using this evaluation method when coupled with a derivative-free simulation-based optimization method, instead we do something that's more sophisticated and more computationally efficient. We use multi-start stochastic gradient ascent, where the stochastic gradient estimator that we use is developed using two ideas. The first idea is infinitesimal perturbation analysis. This lets us exchange the gradient and the expectation operator that defines the gradient of the acquisition function. It lets us exchange these two operators to write that gradient as the expectation of the gradient of a random function. If we can efficiently sample this gradient of a random function, that will be an unbiased estimator that we can then use inside of stochastic gradient ascent. The second idea is the envelope theorem, which allows us to compute this inner gradient more efficiently. This quantity is the gradient of the minimum of the posterior mean as a function of both exogenous noise from the simulator and where we sample. As we change where we sample implicitly inside the gradient operator, the location that minimizes the posterior mean changes. And in general, we might need to worry about the fact that that change occurs. What the envelope theorem tells us is that actually we can ignore that and take that minimizer to be fixed for each replication. That saves a significant amount of computational effort. It means that we only need to minimize the posterior once per simulation replication. So let's step back up and look at how this method performs on an example problem in relation to expected improvement, DEI. On the left, you have DKG, and on the right, you have DEI, starting from the same posterior distribution, and in the bottom row, I'm picturing the acquisition function. The main difference in behavior you see from these two methods comes about in how they think about evaluating points that are far away from previously evaluated points. If you evaluate the function and its gradient at a point like this, it changes the posterior significantly, not just where you sample, but also in the nearby area. And in particular, what tends to happen is that the minimum of the posterior mean will either be to the right or to the left of where you sample. Not exactly where you sample, but to the right or to the left, depending on the sign of the gradient. DKG thinks about that and puts a lot of value on sampling at such points. whereas expected improvement thinks only about the change in the posterior distribution at the point you sample. As a consequence, DKG tends to sample much more at points further away from previously evaluated points. We see that in the first sample, where DKG wants to evaluate here, but DEI wants to evaluate here, refining this local minimum. After one sample, DKG has substantially more information about the function over the full extent of the feasible domain, whereas DEI doesn't. At this point, DEI does a more exploratory evaluation, but KG is already one step ahead. And with this evaluation, reveals a new local minimum that's better than the previous local minimum. After a few more evaluations, DKG has evaluated over a much broader extent of the feasible domain and has found a point that's better than the best point found by expected improvement. In addition to this kind of qualitative analysis, we've also done theoretical work, and we've shown that the DKG algorithm is consistent in the sense that in the limit as you take an infinite number of samples, and if you have a finite feasible domain, the solution to the optimization problem that you get using the knowledge gradient acquisition function converges to the global optimum of the function. DKG is also flexible. We can incorporate biased gradient observations using ideas from multitask Bayesian optimization and incomplete gradient observations, in particular observations of single partial derivatives. I'm now going to hand it to Andrew, who's going to talk about experiments.
Thanks, Peter. So we tested derivative-enabled knowledge gradient on a number of popular optimization benchmarks, comparing to several zero and first-order alternatives, including the derivative-enabled expected improvement and derivative-enabled UCB, showing generally improved performance. We don't win on one of these experiments, but you can't win everything. We also considered a number of automatic hyperparameter tuning applications involving neural networks, logistic regression, k-nearest neighbors, and spectral mixture kernel learning, showcasing various different qualitative properties. For example, the neural network problem is a black box optimization problem. The spectral mixture kernel learning problem involves an expensive closed form objective for which it doesn't take a lot of additional computational expense to measure derivatives. Again, showing quite promising performance for DKG. In summary, derivatives can make Bayesian optimization much faster so long as we use the right acquisition function. There have been three key obstacles to using derivatives with Bayesian optimization. One, the ability to measure derivatives. Two, expense in measuring derivatives. And three, expensive Gaussian process inference. In parallel, the community has been making great progress in each of these directions, harmonizing with our work on how to best use derivative information to speed up Bayesian optimization. In the future, we can imagine a time when Bayesian optimization with gradients is applicable to inexpensive objectives where standard gradient-based optimizers are used today, but with faster convergence and robustness to multimodality. Thank you.
Fantastic talk. So we have time for one question.
Yep.
So this method seems to sample points more far apart, exploiting the directional derivatives. What happens if I mess up the bandwidth of my Gaussian process and now I don't want to make big jumps because I might miss my minima?
Your question was, what happens if I mess up the kernel covariance parameters in my GP?
Yeah, or something like that.
Yeah, so as with all Bayesian optimization methods, there is sensitivity to how well you do inference in your GP. There are two kinds of problems that tend to happen. So one is if you estimate the length scale in your GP so that you think the function is more wiggly than it really is, then that tends to incur a small overhead in terms of how many samples you need to take, but it's not catastrophic. If, on the other hand, you assume the function is flatter than it really is, you can really miss local optima. So a good thing that you should do, both with our methodology and in general when using Bayesian optimization, is you shouldn't just use a map estimator of any hyperparameters. Instead, you should do full Bayesian inference over those hyperparameters.
The question was more in the sense of if I mess up my scale and I get gradients that are very much sharper, including them in the acquisition function might give me more noise in my estimation of where the minima is.
Sure. I mean, that might be true, but generally it's good to condition on as much information as possible, and we are accommodating for the fact that the gradients could be quite noisy. So generally we'll still see an improvement.
Okay.
Thanks.
Let's thank the speakers again.